live webinar. And tire mounting systems, kind of the purpose behind this is tire mounting systems are one of the areas of maintenance on kilns and dryers that is the most prevalent of the problems that we have out there in maintaining equipment. So first of all, what we want to do is want to talk about myself. My name is John Ross, and I've been with IKD for the last 4.5 years, and I have 30 years of experience, 30-plus years of experience in servicing rotary equipment like kilns, dryers, and ball mills. I've been an instructor, an OEM certified instructor for the past 20 years, and done a lot of alignment work and so forth. What I'll be doing is acting as an interviewer of Roland Sutter, who is our chief engineer here at Industrial Kiln Dryer, and he's a mechanical engineer, has 43-plus years of experience designing, fabricating, installing, troubleshooting kilns, dryers, ball mills, other line processing equipment, hydration systems, slaking systems, rotary incinerators, and rotary digesters. He has a great work experience with different companies, from Vulcan Iron Works to Alice Chalmers and Kennedy Van Somm, and is a kiln alignment theory expert, author, and publisher of a lot of information on rotary equipment. So today, with the rules of the webinar, we're again, this is our first year doing this, and we're working towards giving you guys a better product out there. One of the things I want to mention to you is that this session will be recorded and downloaded to our YouTube page, IKD YouTube page, and it will be able to be viewed at a later date by yourselves or anyone in your companies. If you do have any technical questions or anything at all, there's a toll-free number that you can call there. And one of the things that we'll talk about is that we're going to run through this webinar in kind of entirety, and then at the end of the session, what we'll do is we'll have a question answering period where if you would type in your question, we'll go ahead and kind of answer questions in the sequence that they are asked. Anyway, that's the basic rules for what we're going to be talking about today. So what I'd like to do, introduce Roland Sutter here, and the first things we're going to talk about today is tire creep. And Roland, could you give us a little bit of background what tire creep is and why it's important?
Okay, John. Welcome. Basically, we're talking about conventional tire mounting systems, which there's a clearance between the ID of the tire and the OD of the tire pads or support pads. And we do this so that we don't get a compression of the shell if there's inadequate clearance. And how you can tell whether you have clearance or not is as the kiln is rotating, it'll drive the tire, and due to this clearance, you'll get the tire rotating at less displacement than the shell. And if you put a chalk mark on the shell and one on the tire and go one revolution around, you'll see that those points separate. And essentially, that's what we call creep. This is for the conventional tire mounting systems on, I would say, 99% of the kilns and dryers built. Another pictorial that is, you have a gap at the top because by design you're trying to not compress the shell, as the tire will operate like 200 degrees cooler than the shell. So due to differential expansion, that gap is required. And the creep is shown there in the right-hand, lower right-hand corner. There's two marks that I suggest that you put on the shell and tire. Okay, essentially what's happening here, since the OD, or the ID of the tire, is larger than the OD of the shell, it just works like an internal gear. In other words, the pinion in the center there would rotate several times to move the tire a much less rotation. So really it's the difference between the, so to speak, the radius of the shell and the OD, I mean the ID of the tire. That's what really creates creep.
Okay. Roland, so let's talk about this creep and why creep is important. You've touched on a few things, but let's talk a little bit about what excessive creep can do to a kiln shell or a dryer shell for that matter.
Okay. Essentially what we're talking about is due to the fact that you will have creep, or you should have creep, while operating your kiln. If you don't have creep, that means that the tire is compressing the shell, which can lead to fatigue failures in the shell. And if you have a refractory in the unit, if it's a rotary kiln, it can actually have the compression fail the refractory can start falling out. And this can happen also if you start up a unit too fast, and the tire is at a ambient temperature 70 degrees, and the shell heats up rapidly. You can heat up that clearance and collapse the shell. And you can actually, I've seen in cases where this issue is actually, you could actually see where the shell collapsed under the tire. Okay, we talked about actually collapsing the shell. You can also get fatigue cracks. And this little diagram here shows that if you mark a point A on the bottom of the shell where the radius of the tire, which is the shell actually is in good contact with the tire ID, there won't be much deformation in the shell. But as the shell rotates inside of the tire, you go to point B, the shell will flatten at the top. So that'd be the same thing if you took a piece of metal and kept working it back and forth, and eventually it would fail. So, so you not only collapse the shell, you can also start fatigue cracks if this was too excessive clearance. This is just a diagram of when we talk about tire gap, and you can see on the left-hand side at the bottom, usually the contact between the shell and the tire would be more than 180 degrees, but you're going to develop a gap at the top. So every time it goes around, it's going to go through that flexure.
One of the things that I learned too early on was that the actual movement only occurs, if you look on this diagram at the lower left corner, between X and Y, because the shell is actually identical to the tire at the points between X and Y, but on the top of the shell is where the gap occurs, so that is where you get all your creep. Okay,
this is a picture, actually, an an analysis we did on a job where they had insufficient gap. And you can see that it compresses the shell, resulted in a permanent compression. And really what a tire will do if you don't have an adequate gap, it'll make its own gap. This happened, it can happen in two ways. If you, like I said, if you start the heat up process too quickly, you'll get this kind of action, and then you'll say, oh, there's no creep, and then all of a sudden 2 days later you go out and check it, you got excessive creep. So you know, it is very important that that gap be established.
Roland, one of the things that I noticed too in the field when we have a situation like this where it has compressed the shell like that, that typically what happened, the tire heated up too, or the shell heated up too fast, collapsed the shell. So the gap that you have now after that shell is collapsed is 2 to 3 times larger than what the original creep was.
Right. So how do we determine what that temperature is, the difference between the tire and the shell? Well, today you have what I feel very inexpensive thermal imaging. And you can see over there on the right-hand side, the darker section, that's the tire. And if you move over, you can sort of see the tire pads are at a higher temperature. So you can actually measure the differential temperature between the tire and the shell. And you know, it's not a very expensive instrument. And if you were to ask us to come out and repad a shell, we would need that data to do it properly. Otherwise, we'd be just guessing, and we don't want to go there.
And if you're ever in the situation where you need to repad a tire, what that temperature that you need is the average temperature that you're running. It's nice to have minimum and maximum, but you should be monitoring your temperatures throughout the year so that you're dealing with the temperature that this unit's going to be running at most normally.
Yeah, and John, this also you have to be careful, because when you if you have refractory in the kiln, or even in some dryers, it's going to vary as the thickness of the refractory keeps decreasing. The differential temperature is going to increase. If you get a coating inside of the kiln, which happens in some applications, the temperature differential will decrease. So you might go out there and shoot it one day on a windy day in the winter and get one reading, and the next day something happened inside of the kiln and the temperatures are different. So it's good to, you know, all you got to do is walk by these and it records it for you. So, you know, I would recommend you do it like at various times. If it was me, if I do a walk by, every time I did a walk by the kiln, I shoot tire, shoot shell on both sides. And that's good data for your information and for whoever's doing a repad job.
And that's an important point, Roland, that in a lot of times when we take creep readings or we take a valdi readings, or even on a bigger scale, we take shell readings for hot kiln alignments and so forth. It depends on what the kiln is operating on that day that you take that. So it's only a snapshot of that particular day when you take those readings, and you may have to take more than a few to get a better picture of what's going on with the kiln.
Yeah, and you can put this in your computer and do a trending on it and see spikes. And but you know, when you do a repad job, you know, to be successful and be a satisfied operator, you really have to go through this process.
Okay, this is a good question. What is a correct cold gap? What are some of the factors that you figure into determining what gap should be at the hot pier versus the cold pier and so forth?
Yeah, as we said, we need some data to do the correct, get the correct results. And once we know what the what I like to say, the highest differential temperature between the tire and the shell, we can go through some relatively simple calculations and figure out what the thermal expansion is of the shell, what the thermal expansion of the tire is, and then go through some relatively easy math and figure out what the gap should be. And then, on top of that, we'd probably want to be on the safe side, and we'd never want to have any more than an 8-inch gap. So it's just a relatively simple calculation, but I must advise you that actually doing it in the field is not that simple. Takes some skill.
That's a good point, Roland, because having done a number of these, one of the things that you have is it would be nice to think that these shell remain true circles or true to form, and they never do. There's blisters, there's hot spots, there's different things that affect the overall percentage of that gap and so forth. This, can you explain what this is? This is kind of what they call a gap creep graph, and kind of walk us through what this is all about, Roland.
Yeah, John, this is simply, the gap, as John said, is on the top. And another place where too many people want to go on a hot kiln shell. So it's a little device that it simply has a magnet on it that goes on the side of the tire, and you put a piece of paper and a holder on that magnet. And then there's a magnet that holds the pointing device to the shell. Okay, so as this goes around, as we said, there would be no gap at the bottom. That's if you look at that old graph at the top, that's what you'll see on that piece of paper. There'll be no gap at the bottom, and all of a sudden, as you go around, rotate the unit, the gap you'll see the high point, which is the gap at the top. You like to do this 3-4 times to make sure you're getting a reasonable sense of what the gap actually is. And it actually gives you a physical dimension of what the gap is. Another picture here on the right-hand side is a picture of the device that as it's viewed there, you can see the plate with the paper on it and the pointer. So it's kind of an easy way of measuring gap. There's other things to look for, rub marks on the side of the tires, but this is a good way of doing it. It's not a very expensive instrument.
Roland makes a point that it is, if you look at the very bottom of the tire, as before it's down here at the 6 o'clock position, if you have a fairly large amount of gap, you'll see a rub mark right here in this position, which will give you an idea of how much gap you have at top. Okay, I guess one of the reasons why we're talking about creep is because one of the factors, especially on a refractory lined unit like this, is what the ovality is on the shell. And could you give us a little bit of background on what oval measurements are all about, Roland?
Yeah, essentially, when we design a tire, it has a relatively high load on it between the rollers and the tires. And there will be some ovality, or squatting, so to speak, of the tire due to this load. And on this picture depicted on the right-hand side if you got the dimension, horizontal dimension, DH, and the vertical dimension, DV, you could measure how much this tire is, so to speak, squatting or going out around just due to load. And you can get through it. It's usually expressed in percent. Excuse me. So there's a little formula down at the bottom there. We just take the difference between the horizontal dimension, vertical dimension, and divide it by the ID of the shell. And that's what we call ovality. So that's a number which is controlled by the tire thickness. So as we talked about, you want to get the correct gap, because if we have too much gap, you can see in this picture that there's a deformation in the tire, and as I said before, every time the unit goes around, eventually it's going to flex, and that's what causes fatigue cracks. So many years ago, a company called Holderbank came up with a measuring device called the valdi meter. And what you do with this, and John's done it many times, is it has magnets on it. You put it on the shell. You have to do this while it's running hot. And it has a pencil on it again, the spring, and a round polar chart. Okay. So as this goes around in the revolution, what it does is it measures the slope of the shell. It really doesn't measure diameters. It's just measuring the distance between those magnets, which is usually 1 meter. Okay. And as it goes around, the plunger goes in and out, and it's actually just measuring the flatness of the shell or the roundness, whichever way you want to look at it. So that's, then it'll scribe, if you look down in the lower right-hand corner, you'll see what kind of a picture it gives you. So in this picture, it's pretty bad shape. It's flat at the top, okay? And then you can see it's kind of round down towards where the tire would be, supporting the shell. And then in this case, there's 2 bumps on it. That's where the tire's bending due to the load of the roller. So it gives you a pretty good idea of 2 things. What the ovality is the shell due to the gap that you have, and also it tells you that gives you an indication of how the particular tire is being loaded, which is really not part of this discussion, but it's other information you get.
This is kind of just a picture of the ovality beam as it is, and one of the things that they do, what you do to get a good cross-sectional view of this is you want to measure it in 3 spots on the cross-section of the shell.
Yeah, and John, over on the left-hand side, there's a different way of measuring this. You can do it electronically with a transmitter, but it tells you the same thing. As that slope of that line starts on the left-hand side coming up, that's telling you when that line's straight that there's very little difference in slope, which basically means the tire's supporting the shell well. And then when you get to the top, you can see a flat lines up there. It didn't die, but it's flatlining. Essentially that's telling you the shell, as the gap has created a relatively large flat spot, which is this flexing we're talking about results.
And this is just an example of the charts like we use for determining what the ovality is on it, and you have the 3 measurements here on the chart, and it'll give you a correlation of what is happening during the course of a revolution.
And know, our experience, we pretty well know what kind of, what range that ovality meter should, you know, predict the ovality. And basically, as a graph on here, giving you an idea, it's a function of the diameter of the kiln or dryer, it doesn't really matter. And the percent ovality. So we pretty well know what acceptable range we have to stay within.
And when the holder bank, from what I understand, Roland, when the holder bank originally designed this thing, they used some empirical data to determine what percentage of ovality was acceptable per the diameter of shell. So there's a lot of charts to compare this to, so that you know that your tire's in the range that it should be.
Yeah, and on kilns, it's, you know, critical with regards to refractory failure, and that probably is the one item that determines what the percent ovality is acceptable.
Even though we're talking a little bit heavily right here on kilns, the one thing about all this movement and all this flexing of the shell that occurs even on dryers is what Roland previously mentioned about fatigue type failure and cracking that occurs in the shell. So even if you have a dryer and you have wrapper bands and thicker shell underneath the tire, if you get a lot of this flexing that occurs, you would see a lot of fatigue type cracking that occurs.
Yeah, and John, even if it's a dryer, obviously we're going to slim down the tires and the rollers because of less load. So the generally a dryer doesn't have as rigid a shell design, and you know, probably can take a lot more ovality before you get a failure. But still, it's something you should consider keeping track of.
And with that in mind, Roland, one of the things that I've seen out there is a lot of customers and end users will do a lot of resurfacing and grinding of the tires to get the contact surface. But over a period of time, this is going to affect the thickness of that tire and create ovality situations.
Absolutely. I've seen that go so far, and tires fail. I've seen them take off as much as an inch of material over the years. And then they're, and John and I both have stories of problems that occurred. It'd be too lengthy to go into here, but it happens.
Okay, on this slide here, we just a few examples of what's going on with the different types of ovality that you can see. And one thing that's kind of cool is that ovality readings can give you an indication of what the alignment is on the unit as well. So like if you have these rollers, for example, showing a large indentation, it might be that this pier is overloaded, right? And then these examples would be basically your rollers could have been shifted to the left. So a lot of pressure on one roller and not so much on another, which, you know, obviously you can't see, but you can measure. Okay, now we're that was a lengthy approach to get to tire pad mounting systems. Explain to us what a floating adjustable tire pad system is.
Yeah, first, John, we should say that most kilns originally manufactured, the tire pads are welded onto the shell. The shell is machined to a certain diameter to get the right clearance. And then over the years, the pads will start wearing, the gap will start increasing. And what do? You can't really cut the shell out and send it back to a shop and get it machined. So, not only us, but other people in the service business use what we call the floating tire system. And I'll get into a little bit more detail, but essentially you have to take out the old pads, and usually it's a real pain getting the weld underneath the tire, but you got to get that done, get it all ground down so you have a smooth shell. And then you slip these pads in the gap between the tire and the shell. And there's a process we go through, which we won't get into, but getting the right clearance. So you put those pads in. And then on alternating sides, we put weld tire stop blocks. So you can see they're on one side, next one they're on the other side. And why do we do this? That's so that we can get underneath that pad and put shims in so we can adjust the clearance. And then you can see that also we have to retain the tire pad so that it doesn't fall out. So we put tire pad stop blocks or sport pad stop blocks in place and weld them in. And then on either side of that, so they don't rotate, we weld in blocks so that you don't get a motion circumferentially. We'll talk about this a little bit later, but one problem that happens that due to the differential motion between the shell and the tire, we sometimes have to put a sacrificial ring in of soft material so you don't damage the tire. We'll talk about that a little later. There's no need for that if you have the right maintenance procedure. So these are just some pictures of the same design. One thing you want to do is, since once again the tire is rotating at a different displacement than the shell, you need a gap on the side so you don't wear out those retaining pads. And like I say, the pads are not welded to the shell. One of the things that used to happen, they're welded to the shell, and they keep flexing, and you'd have weld failures, shell failures created by the pads. With these loose pads, they don't really, they're just like you're running a Caterpillar across the road and then you put down a mat. I mean, same basic idea. They flex, they move, they don't put a lot of stress into the shell.
On some of the older kilns, I remember that you could get up to a foot of overall stretch in the kiln just from the cold to the hot conditions. So any time that the kiln was elongating or stretching as a result of starting up and getting hot, when those pads were welded, it really put a lot of stress on the welds.
It's just a layout of, we have to do some engineering to get the right spacing, so we want to make those pads as wide as we can. A lot of times you use like 8-inch wide pads, and it really doesn't work as well. It should be around 12, John?
Yeah, the wider the pad, the floating system actually works much better on larger diameters than smaller diameters. And the reason why is because you can go with wider pads. And if you have too small of a diameter, you have to have a really sharp radius or curve in it, and it makes it hard to do wider pads. So it really is a more effective system on larger diameters.
Just a picture of an in-progress pad system being installed. And once again, it takes a little bit of experience when you're shimming these pads to get the right clearance. Because obviously the kiln's sitting down on the bottom of the tire and all the gaps at the top, so you have to judge from that information how much to shim.
This is true, Roland. It actually is, you're working at points similar to what you would tighten a hub on a wheel or anything. You've got to work around that so you distribute it equally all the way around. One
thing that happens on tire pads, and just a good example of it. If you have a high-speed application like a dryer or some of the new cement kilns that run like 3 RPM, although I've seen floating tire pads that work 3 RPM on an 18-foot kiln, one of the, if they flop too much or clunk or whatever you want to call it, they will move. They'll be loose at the top and then tight at the bottom. But sometimes it's a good idea to just weld one end of the pad and leave the other end free for shimming. So this is what we call a semi-floating pad system.
And this is one that, for me personally, that I've seen rolling is that this works well on a dryer system, because then you can go with the narrower pad and not worry about it getting flopping around loose in like a floating system, because you do have one end trapped, and you're not dealing with the real high temperatures to speak of. So, and
one thing that I would like to bring up is you'll see that everything except every other design that we've shown you, everything is radiused in the corners. I didn't do it on this one to illustrate that if you have a sharp corner in the pad when you weld it to the shell, that's where the cracks usually start. That's a stress riser, and just about every time the shell will crack from that point.
And that's a good point, because I think when we're talking about, if you let these things go for long enough that you really create a high clearance, then if you have a system like this, they become even more vulnerable because of all the shell flexing.
Right. Because once again, when it's at the bottom of the shell, it's seeing all the load. When it gets to the top of the shell, there's no load on them pads at all, and it just pushes them in, and then they bounce back out, and that's obviously what we call fatigue.
Explain this with, well, I just to kind of brief you, is on a lot of drying, cooling equipment, years past they would put a wedge and shoe design in there, which the idea behind it was to hold the tire tight and not let it to rotate, or to keep the creep down. Those systems didn't work very well, and this is kind of something that we're throwing out here. It's an adjustable wedge system so that you can adjust the tightness of the tire and keep this thing out. And I've seen it where you actually have a torque specification on here to really maintain the same amount of torque on all the wedges. You want to talk any more about that?
Well, basically, we had to come up with a scheme where we work on low temperature applications, high speed, smaller units, where temperature wasn't really a big issue, but it was still an issue. And this is upfront cost in a system like this is relatively high, because the wedges shown on there have to be machined to the diameter, the ID of the tire, their mating surfaces, and the OD of the shell. So essentially, we have to lock these in. So on the left-hand side, there's a C-shaped piece that gets welded onto the shell, and on the right-hand side, there's two blocks that get welded onto the shell, just to trap these wedges in so they can't come loose. And basically torque up that bolt, and you can tighten up the tire. I've seen cases where you could tighten that up pretty good. You're still going to get some creep. This will not stop creep, because I've shrunken tires onto shells and they still creep. And I'll illustrate later, there's a tremendous force between a shell and a tire. But anyway, so this is a quick way of making adjustments without shimming, without welding. Like I said, the upfront cost is kind of high, but depending on your application, this may be the answer. You want to explain this, John, as far as what not to do?
Yeah, this kind of comes back into what happens when you go with these really narrow support pads on units. What happens is there's not enough cross-sectional area, and if you don't get everything snugged down tight when you're installing them, what can happen is, like in this case, is this tire passed through the rollers, and when it hit the rollers, it bent the bar, bent the pad. So now that the pad is not no longer, it's bent and it's not really doing an effective job, and it'll jump over these end blocks, and it causes a lot of issues mechanically.
And John, the other thing we wanted to illustrate here is that on the sides of the tires, you'll get the tire pads wearing into the side of the tire. And a lot of people think the solution to that is to skew your rollers different, but it really isn't. This problem is generally remedied by getting the slope of the base on line in the proper position so that you don't get tire block wear. So it's kind of important that you have your bases and rollers on the correct slope. So you might want to reroute your bases and check out the slope. So to summarize what we've been talking about, we believe that for repadding, the floating pad system is good for lower speed units, for high temperature applications, where we can reshim. For the dryers, the semi-floating pad system I think is the best. And of course, if there's many applications that we'd have to look at, the tapered shim is probably the best overall system if you can use it.
Okay, one of the things that brings us into things, since this is such a problem in the industry with the wear and the wear rate on all these tire mounting systems, in your opinion, what should we do for lubrication?
Well, definitely what you want to do is lubricate the bore of the tire with a bar that will melt due to the shell temperature, and that'll lubricate the pads, and that'll really slow down the rate of wear on your tire pads and reduce the development of a high gap, high creep. So there are what we call lube blocks that you stick in between the tire and the shell, which will take care of that problem. So we absolutely recommend this. And then on the side of the tires, you can't do this, so you can use a spray type system to get lubricant between the stop blocks in the tire. You can also use this on the bore if you guys don't really want to put blocks between the tire and the shell for safety reasons.
Yeah, and the other thing is on a dryer, usually, or dryer cooler or something like that, you usually don't have the temperature to melt the blocks, so you actually need to use a spray system to lubricate the ID on the tire.
And what you don't want to do is put a lubricant on there that picks up dirt and dust. Whatever the lubricant in, it's a metal type lubricant with a emulsified carrier. When you spray it on, you got to get rid of anything that can cause dust or dirt to get in that bore, because obviously it's not a good idea.
Okay, we're gonna run through these slides a little bit quick because we're kind of running out of time, and it's more lubrication's kind of more of a whole side issue in itself. But lubricating tires and rollers is always important to retard the wear that you have. And if you look at the face of a tire and roller, you get a lot of microscopic spalling, pitting, and so forth if you don't have proper lubrication.
Which is generally graphite.
Right.
So it shows the same thing.
Yeah. Okay. All right. So why don't you give us a rundown on what we should be doing to check this and assist with the tire?
Well, essentially, I would, if it was my kiln, I'd check the creep every day. I'd measure at the same time, measure tire temperatures, shell temperatures, and check the graphite blocks, pull them out. If they're glazed, always just take a wire brush and clean off the glaze and put them back in. Make sure they're applying graphite to the tire. Usually if you see a shiny tire, you're not getting lubrication. If you saw a dull look, you're getting decent lubrication. It should be uniform. Lubricate. And this is what happens if you get a piece of weld slag or other material between the pads and the shell. And you can see the tremendous force you can get gouging out a tire pad and actually breaking them off.
One of the things that happens on these is if you get a lot of forces in here and an incorrect installation of the tire, or these tire mounting systems, you'll get what we call slugging, where the tire actually digs into the pad or the filler bar and pulls out chunks of metal. And that's what they call slugging. And that's a bad situation.
That's another picture of the tire pad that you just saw.
Okay, we're going to open it up for questions. So basically what we'll do is if you want to go ahead and write out your question, we'll answer them. And any questions that you have, we're open to them right now. Okay, we're working on this. One of the questions from Dave Stewart is, are there any continuous monitoring systems for a problem? Roland, you want to answer that one, or do we have a continuous monitoring other than creep? Or for a problem?
I think we have that under development, where we're trying to, get a signal back to a control room so you can trend your tire creep and temperatures, or use cameras to do that. That can be sent back to your DCS or your computer system. So if there's some interest in that, we could move forward on it. But right now, we don't have anything. But if there's some interest, we definitely could develop that.
Okay, how does this equate to vibration? Are there any continuous monitoring systems to monitor for a problem on vibration, like a vibration sensor?
Yes, you can use vibration sensors. My experience is most of the vibration comes from the gear system rather than the tires. Yes, there are systems available for that.
Are there any more questions? Okay. What I'm going to do is since we got a little time, is I'm going to open up your guys's open up you guys' speakers if you want to talk and ask questions on. Any questions? Oh. Filler bar materials. Carlos Cardenas. Filler bar materials. Usually filler bar materials are made out of an A36 type plate, a mild steel. The idea is that you would rather the filler bar wear versus the tire wear. So you don't want to damage the tire, so you basically would use a softer, mild steel to make those filler bars out of. Okay. And also, one of the things you can do, we will post this on our YouTube, and if you have any questions at all that you would like to write out and send in to us, there's a couple of different ways you can address us to the representative, the IKD representative, and we also have online what we call Ask the Expert. And Ask the Expert basically is you can go ahead and ask us whatever questions. We have another question here from Justin Hayes. How did you determine the minimum thickness a tire should be? We have an old kiln that has had the tire ground multiple times. This is a small kiln, roughly 7 foot 7 inches. You want to answer that, Roland?
Well, essentially, to do it the correct way, we'd need to estimate what kind of loads you have, what the roller diameter and tire diameter is, and we can stress that out and tell you whether you're in a critical area. Generally, tires are somewhat over-designed because they're designed for not to get high ovality rather than stress. So, if we had some basic information, we could let you know.
Okay, another question by Dave Stewart. Is this more of a problem with SS shells than with CS shells? Stainless steel versus carbon shells? You want to answer that, Roland?
I really don't think there's any real difference. One thing I will say about stainless steel has a tendency to gall against carbon steel. So sometimes you can get some galling between the tire and the shell, and I highly recommend that you use a lubricant in that application. But, obviously stainless expands a heck of a lot more than carbon steel, so you'll have a higher gap to get the right conditions. Higher cold gap, rather.
Any more questions? We sure appreciate you all coming in and joining us today. We would welcome any of your input on what we can do to make this better, and we will have this on, as I said before, we'll have this on the YouTube, so if you found it valuable to yourself, pass it on to someone that you know in your plant. And we, to all of you that registered here today, we'll send out the link to our YouTube that will give you access to this webinar and the other webinars we've done throughout the year. Again, thank you very much for your attendance. We appreciate it. And thank you, Roland.
Thanks a lot.